All right, welcome everyone. This is Steve with Aptera Owners Club. I'm joined by Tim, and Tim is the battery lead engineer at Aptera. Tim, can you kind of introduce yourself? Tell us what your actual position is and what you do at Aptera.
Sure, thank you. Nice to see all of you guys, at least vicariously via this interview. I'm the director of battery and special projects, and what that means is I have overall responsibility for the battery system development and production of the battery system at Aptera. And then, as far as special projects are concerned, we'll branch off into certain areas, maybe interesting solar activities with our solar technology and anything else interesting that comes up that I can participate in. I'm tasked with doing that pretty regularly. So I joined Aptera not long ago. I think it was February. After working with Steve at Flux Power for a while. So some years ago, before Steve started Aptera, he joined us at Flux for a while to help us out, get us out of a pinch, and help me with running production while I focused on engineering there. And he and I exchanged ideas and discussed his passion for this project, this vehicle. And over the years of working, actually, I think it was probably only 2 years working with Steve, I became quite interested in what he was doing and thought it was really exciting. And eventually, he ended up renting some warehouse space from Flux Power and building the the Noir vehicle at at our facility. So I got to eavesdrop on that a little bit and get some early
Okay.
glimpses.
So that was like the reboot of Aptera. He was making the Noir
Yeah.
vehicle. So this was in like
Yes.
2018, 2019, that around that time. Is
Yep.
that right?
Yep.
Okay.
Yes. The years kind of blend together, but pre-COVID.
Yeah, yeah, okay, yeah. So yeah, that's a good way of like kind of keeping the year straight. We
It
definitely
is.
there's like
Yeah.
a interesting timeline there. So yeah, so he was building it there. You guys got to become friends, and then you decided to join Aptera several months ago. What made you
Yes.
decide to join?
Oh, it wasn't the risky nature of a startup. It was it was many of the characteristics of a startup though that piqued my interest. I really enjoy being able to wear a number of hats and exercise a variety of skills and participate in development as well as fabrication and manufacturing activities. So I anticipated that there would be a lot of that, and in fact, there certainly is. But at the same time, I was truly interested in the vehicle. I actually started and my awareness of the vehicle was with the first Aptera. A young engineer that I had hired told me one day that he had put $1,000 deposit on this strange looking vehicle. So I looked into it, and at the time I thought, wow, that's not quite for me because I had a pickup truck at the time and I was used to that utility. But what I saw that really interested me is the possibility of having truly phenomenal mileage in a vehicle and not carrying around a lot of excess. And the simplicity and elegance of the early vehicle got me interested in it. So when it started up again, I had already been exposed to it initially, and I thought, oh, this is really strange. I'm working with the guy Steve who had this idea so many years ago that I thought was cool.
Hmm.
Just happened to end up working with him at Flux.
Yeah, yeah. All right, then you had then there was a positioning opening up at Aptera, and then you decided like, hey, this sounds like a good fit.
Right.
So when you joined Aptera, they already had kind of a battery pack designed and engineered, right? Like,
Correct. Yes.
what are the challenges in making a battery pack for the Aptera? And like, how come we don't use like how come we don't use like a battery pack from Toyota or Hyundai or GM or Lucid or Tesla or something like that?
Well, maybe the snide response to that question is because they won't sell it to us, but
Okay.
uh, the reality is maybe a little more subtle. Thankfully, like you said, they had already designed the battery, so much of the heavy lifting was already done by the time I joined. Really, my focus has been on refinements to the design as I've built prototypes. I'm identifying things that can be done in a manner that make it easier to manufacture, more cost effective, and also slight adaptation to a variety of different cell types that we might want to use. So the type of challenges the team faced before I joined, they were really they had to design a battery into a space that is very much different than most automotive batteries. It is kind of a pancake shape, of course, like most of them,
Hmm.
but it's narrower and it has very tight space constraints. So the components, like the power distribution unit, the BMS, the electronics that control it, those have to be placed in a unique position to accommodate the shape of the body surrounding it. So
Mm.
that really sort of paints a picture of a unique battery design that's bespoke to this vehicle. Now, there are companies out there who do make batteries to sell them to people, versus Lucid, for example, they make batteries to sell vehicles and they're not going to share them with other folks unless it's a Formula race car that they happen to
Right.
make batteries for. Companies like Webasto, for example, they make fantastic batteries. They are um, similar in voltage, can be similar in capacity to what we have, but they're specifically designed for industrial applications like buses or heavy equipment. And the packaging efficiency doesn't meet our requirements. Our requirements also involve some level of participation in the crash protection of the vehicle. So the battery is used as a structural element in the vehicle, much like it is in a lot of other vehicles,
Hmm.
structural, but the structural characteristics have to be tailored specifically to the Aptera vehicle in this case.
Mm. I see. I see. Um, so I noticed that in the latest videos of the Aptera, the bus bars, they look really cool. They're very. I think I thought they were very elegantly designed as a non-engineer. Was it like that before you joined up, or was that one of the things that you kind of helped refine?
I wish I could take credit for that, but no, the only thing I did was bend them
I
into
see.
that shape. The
Okay.
design was already done. It is a very elegant design. It lends itself quite readily to a very efficient laser welding
Hmm.
system.
Yeah.
Um, that said, we're also pursuing options with wire bonding, which is technology used across the automotive board as well.
Right.
And benefits of wire bonding is that it can afford us some more flexibility in terms of using different cell manufacturers' cells
Mm.
and not having to optimize the process to the specific cell as you would have to do with laser welding.
Okay.
So we're
Are the
working on both in parallel.
are the form factors different between like because they're all 21,700 cells, right? So
Correct.
is it because the like the anode is like a slightly different width or something in different manufacturers, or are you talking about totally different cell chemistries and different form factors?
Well, no, they're all the same chemistry. The cells we're considering at this point are all the same chemistry, but the the cathode shape, which is like the little button at the top of a button cell,
Mm.
those are subtly different from cell to cell, though very subtly. And in fact, it probably wouldn't make any difference. But
Mhm.
on the anode side, because we've opted to connect to the shoulder of the battery as
Yeah,
opposed to say the bottom of the battery for the anode connection, um, the subtle differences in curvature of the anode where they crimp the can together, those really do play a big part in how the laser welding has to be tuned.
I
So
see.
it's important also in wire bonding, and that's probably where you see the bulk of difference between cell brands.
Okay, because I noticed like w when there's a video about Peter Rawlinson going through the battery pack for Lucid, and they use wire bonding which looks like it
Mhm.
would be way more labor intensive or slower. But
It is.
is that not true, or is that true?
No, that's definitely true. I don't know the specifics with any level of certainty, but I think approximately twice as laser welding is twice as fast
I see.
uh, compared to wire bonding, and the equipment is twice as expensive.
Okay.
So if you're doing laser, you need, let's say, one machine versus two machines for wire bonding.
Mhm.
But like any other process in manufacturing, um, you can make a decision about what your manufacturing footprint's going to look like, and that will be swayed in one direction or the other based on other upstream or downstream processes. So
Mm.
there are some upstream processes that might take time for um, adhesives to cure, for example, before the wire bonding or before the lasering. So it could behoove you to have one long line or two short lines. It depends on, like I said, the up and downstream processes. So I wouldn't say there's any real clear winner, but for an organization of our size, the wire bonding technology is more readily adaptable to any changes we might make in our module, whereas the laser welding, you'd want to focus a bunch of time on perfecting it and then ideally not change it.
Right, right. So you guys are working on both platforms kind of simultaneously as a
Yep.
contingency plan in case like the suppliers need to change or something.
Right. And the first three vehicles that we're building now will have each type of bonding technology used in them. So we'll evaluate the differences actually in the vehicles.
Hmm. Okay. So that's something is that's sounds like something that Aptera does often is like they work on multiple different things in the background to have contingency plans in case like plan A doesn't work out. Um,
Yeah. Well,
that's
you kind of have to do that as a startup company. You
right.
have to plan for suppliers maybe making different decisions than you'd been planning on,
Mhm.
or the engineering pointing in one direction this week and a different direction in the next week based on something we learned.
Right. So, because some people get the impression that like, oh, Aptera changed their plans, now they have to start over again. But really, it's a lot of things have been happening in parallel for a long time.
Yeah.
Okay.
Yes.
All right, great. So what it seems like Aptera is using N cooling. Is that correct?
Yes, it is. Yeah.
And why did we
I
decide to go
think,
N cooling rather than side cooling? And what are the like advantages and disadvantages of both?
well, I will speak for the team who's no longer here.
Okay.
And if I were the one making the decision, I would have made the same one.
Okay.
So end cooling is very simple. When you're building a battery, you have to put it on something, um, and it's probably going to be something stiff. And in that case, for automotive, it's probably going to be aluminum. So you've already got a piece of aluminum occupying the bottom of the cells. Um, so a cooling plate isn't a big stretch from there. And they're very cost effective with low development costs. So we can have a traditional sort of dimpled, as you've probably seen the cooling plates in the models. There's
Mhm.
just sort of a dimpled surface brazed up against a flat sheet of aluminum. Whereas the side cooling, the ribbon cooling, like you'd see in a Model S battery, for example, that's very effective, but it requires a fair bit of development effort, and even Tesla struggled quite a lot getting um, the proximity of the ribbon cooling band tight enough to the profile of the cells to have a good interface. There's a secondary challenge with the ribbon cooling in that the cells have anisotropic heat transfer. They transfer heat better axially than they do radially.
Mm.
So that has to do with the fact that they're just sort of like a wound up roll, sort of think like a paper towel roll,
Mhm.
but coils and coils of copper material rolled up with stuff separating them, insulative layers separating them. So they'll readily conduct heat along the length of those copper sheets,
Mhm.
but not so much through the various layers.
That
So
makes sense.
you can pull a lot of heat out from the side, but you need a lot of contact area. and perfecting that effort to get the contact patch broad enough takes a lot of development, and a lot of investment in tooling to make those micro channel extrusions that are used in the Tesla. So it serves us well to use the end cooling. It is in many cases more effective than the ribbon cooling approach or the side cooling.
Mhm.
But I think fundamentally for us, it just fits the nature of early battery development that we don't have to sink a tremendous amount of R&D effort into side cooling. And side cooling is great for very high performance, also like extremely high charge rates or extreme discharge rates. But the Aptera vehicle isn't designed for that. It's designed for very high efficiency.
Mhm. And it seems like, correct me if I'm wrong, that a lot of the other EV manufacturers are moving to end cooling. Like Tesla, I believe, is using end cooling. Rivian uses end cooling. I think they stack their cells and they have a plate in the
They
middle
do.
that cools them. And
It's
then
very
looks like
efficient.
Lucid
Yeah.
also does end cooling. So it seems like, is that the way that the industry is moving, seems like?
I think as you see the battery manufacturers or the vehicle manufacturers going to the larger and larger format cells, um, that exacerbates the problem with the side cooling because the as the roll gets bigger, it takes longer and longer for the heat to get out of it radially.
Mhm.
But those big fat cells, they're not appreciably taller than the 21700s.
Mhm.
So the heat transfer axially is still quite good. So I think that's probably why you'd see that shift.
I see. Are you at liberty to tell us about suppliers? Like a couple of years ago, they said that Eve Energy was going to be one of the suppliers for the battery cells. Is that still the case? Or are you guys looking at other suppliers, or
We
you're?
are looking at a we are looking at a few, and I'm not at liberty to tell you which ones. I'm sorry.
Got it. No problem. No problem. And then in terms of the end cooling, Chris Anthony mentioned that for the larger capacity cells, there was a plan to use formats of cells that are the same diameter but longer in length to give higher capacity. Um, is that going to be a problem for the end cooling? Because now you have a longer cell and it has to, the heat has to travel a longer distance. Has that been tested, or was it
We
too
have not
early to
tested it
talk
yet.
about that kind of stuff?
Yeah, it is too early because our focus right now is not on the higher capacity pack.
Mhm.
But back to the overall intent of the vehicle, regardless of the size of the battery, the vehicle's still going to have roughly the same power draw when you're driving it down the road. So
Mm,
you don't really need to remove any more heat from the big cells. You just need to do it for longer. I guess that's misspeaking in technical terms. You do need to remove more, but not at a higher rate.
mm,
So the batteries might last for, let's say, I don't know, 8 hours of driving. So you'll be removing heat for 8 hours versus four if we double the capacity of the pack, but you won't be removing it at a higher rate.
okay.
And during driving, the heat removal isn't that critical anyway because the draw is relatively low, so there's negligible heating.
Right. The biggest heating stress would be during DC fast charging, correct?
Correct. Yeah.
Okay. And how is that going to be tested for? Like, are you going to test higher and higher rates and see at which point the pack fails, or how's that done? I'm not familiar with the process of testing for DC fast charging.
Well, you just described it.
Okay.
Yeah, that's exactly what we'll do. So we've already tested the individual modules
Uh,
at a 1C and a slightly over 1C, about a 1.5C rate.
mhm,
And that was done without active cooling. The batteries going into these vehicles will be tested with active cooling. So we'll be able to test them upwards of 2C rate, which is beyond where we plan to charge anyway.
uh-huh. A 2C rate at of a 44 kilowatt hour pack, is that like, are we talking 90 kilowatts? Is that
Yeah,
right?
for those yeah, for those unfamiliar with the C rate nomenclature, um, a 1C rate represents charging a battery from full from empty to full in precisely 1 hour, or discharging it from full to empty. So if you have a little 21700 cell, it has about 5 amp hours of capacity. So if you were to run that thing at 5 amps, either charging it or discharging it, you're running it at 1C. And if you charge it at 10 amps, then you'd be charging it at 2C.
Mhm.
Common for most devices that we're familiar with, like handheld drills and things of that nature, might be anywhere between C/4 or 1C for household use items. And a cell phone, I don't know what those charge at, probably close to C/2.
Mm.
But for vehicles, we want to push them harder because we'll be able to spend less time at the charging station. And generally, if you can get away with about a 30 or 40 minute empty to full cycle, that'll satisfy most applications.
Mhm.
It'd
Mhm.
be just over 1C.
Okay. All right.
Challenges, though, if you go too fast, you do get too much heating, and it also degrades the battery more rapidly.
Right. And having a smaller battery pack allows for 1C charging at a less power draw, right? Because like we have these 250 watt, 250 kilowatt chargers. And then the early DC fast charging was 50 kilowatts, right?
Yep,
And that would be 1C. 50 kilowatts would be 1C for the Aptera.
right.
Okay. All
That's
right.
correct.
Okay. Um, so is the battery pack design now finalized? Are we like 100% finalized and we're just now building and testing, or is it still we still haven't nailed it down yet?
Well, it's as finalized as any good design can be until you build the first prototypes with the production intent tooling.
Hmm.
So we've built a number of modules and systems with prototype tooling,
Hmm.
many of the parts being 3D printed, for example, or cast instead of molded.
Uh-huh.
But the PI builds that are underway now, those will be built with production intent tooling. So
Uh-huh.
the proper aluminum extrusions will be produced. They'll be welded as intended for the production vehicles. All of the materials will be the same as the production vehicle intent, which will then give us an opportunity to test the actual design versus testing some surrogate.
So is the production the battery packs that we saw in the most recent update, are those based on a production intent tooling or are those prototype tooling?
Those were prototype.
Hmm.
uh, the ones that'll go into, so that one that you saw was the aluminum frame was built from rectangular sections that were bolted together and then welded. So it was very much a prototype frame,
Mm.
um, and it was built with modules, though they matched the production shape and material. They were not built on the production like for example, the bus bars or the current collectors, I bent those by hand with a 3D printed fixture.
Mm.
The ones that are built on the production tooling will be from a progressive stamping system,
Okay.
and the injection molding tools will be actual injection molding instead of 3D printed
Okay.
in that case.
So the production intent battery, what do I call it? The battery tray, that thing that was bolted from rectangular things. How will that be built? Will it be forged or
Yep,
stamped
it's
or
extruded aluminum. So
okay.
the
What is that?
frame
I'm not sure
itself.
what that is.
Well, if you've ever seen like aluminum square tubing, for example,
Okay.
or actually maybe a more readily accessible example is a screen door frame or a
Okay.
screen window frame at your house. It's not solid aluminum. It's a very thin wall aluminum shape, and the shape can be relatively complex, like that of a screen door frame or a sliding door frame, for example. Um, and what that allows you to do is create a shape that has a lot of detail in it. It can have very specific external dimensions that will interface with the rest of the vehicle, will give the the strength characteristics that you're looking for in any particular section shape, but then have the inside be largely hollow. So it reduces the weight, which of course is important for efficiency. So these are made by squeezing hot aluminum through very small holes in
Okay,
what are called dies. And those dies are what determine the shape of the extrusion.
I see. Okay, all
So
right.
the frame will be made out of that material, which is then welded together. And stamped aluminum, heat sink, or cooling plates, stamped aluminum covers.
Okay. When are so the battery modules and that the prototype battery tray, is that what's going into the PI, the first drivable PI vehicle? Or okay. When should we expect like production intent tooling, battery packs and battery trays? Is there a timeline for that?
I think we're looking at about 60 or 70 days from this point.
Oh, okay. All right. And so I in the latest video you talked about vibration testing.
Yeah.
What other testing are you guys thinking is planned for the battery packs?
Well, on a pack level, we'll do similar testing, shaking it around, shock, and so forth.
Mhm.
There are various electrical tests to confirm that electrical isolation is up to snuff. The high power cycling of the battery pack will be done in conjunction with cooling
Mhm.
under hot conditions, heating under cold conditions to confirm that the thermal management system can keep the battery under ideal operating conditions.
Mhm.
And then, of course, road testing, um, actual real world driving.
And how long do you think this testing takes in general? Like, does it take 2 months, 6 months, 9 months?
Uh, let's carve out the road testing and
Okay,
not address that because that can take, you will be learning for years about the batteries in the real world.
I see.
The lab type testing, I would think it's probably a few months of testing.
Okay.
Environmental testing can take a fair bit of time to set up. Um, Building environmental chambers to put a whole vehicle in is certainly more involved than just an oven to put a battery in. So those kinds of things could push it out multiple months, I imagine.
Okay. Now you said that when the batteries are you've gotten with pat without any cooling, you can get 1C charging. You've tested that on the modules, and you figure that with active cooling, you could easily get 2C charging. Does that mean that Aptera is planning on allowing for like 100 kilowatt DC fast charging? Or is 50 kilowatts
I,
still the design parameter that we're shooting for?
yeah, I'm not sure I'm prepared to answer that.
Okay.
Not because I'm avoiding sharing any information, but
Mm,
I'd just be more comfortable if we've had an opportunity to test it first.
got it. Got it.
But I don't think that a 2C charge, I think it's worth realizing that you really can't charge from empty to full at 2C. It's
Uh-huh.
just a convenient term that allows you to talk in sort of a unitless number that can apply to from one battery to the next.
Uh-huh.
The reality is when you charge at that rate, the terminal voltage of the cell itself gets rather elevated as you go past 50% or 60% of state of charge. So then you really have to start tapering off the charge rate as you approach the top of charge. So if you pulled up to a fast charge station with a completely empty battery and you're charging it at a 2C rate, you're probably only going to be doing 2C for 15 minutes or 20 minutes.
Right. Kind of in the middle of
And
the battery pack, right?
yeah,
Yeah.
yeah, or mid low end.
Yeah.
Um, so it's not even like you have to pull a tremendous amount of heat away from the thing for a whole half hour. It doesn't last that long.
Right.
But there are a lot of variables in there that we really need to test before we can make any firm commitment about what it's capable of.
Okay. All right. So kind of some potpourri questions, and you can tell us whether or not you can answer these or not. Because these are common questions that people talk about and ask about. Is Aptera thinking about lithium iron phosphate chemistry?
I am. I don't know if Aptera is, but I am.
Okay.
Um, for the past 9 years, I worked with almost exclusively iron phosphate,
Mhm.
and it's compelling for a lot of reasons. Cost is one of them. Not so compelling in a number of regards, like the energy density.
Mhm.
It's not as energy dense as the NMC material is. But there's also the challenges associated with the rare earth metals that go away when it's iron phosphate.
Mhm.
Um, so there's a lot to be gained from that particular chemistry. And as we as a group of consumers become more and more comfortable with what it means to drive an electric vehicle, we'll start thinking differently about really how much range do we need to squeeze into a vehicle? How
Mhm.
important is it? And I learned the lesson for myself a few years ago. I leased a Volkswagen electric Golf, and
Mhm.
beside being one of the funnest cars I'd driven in a long time, it was um, it was sort of frustrating because it was only like an 80-mile range.
Yeah.
Um, and right now I'm driving a used Tesla, so its battery pack is somewhat diminished, but it still gets over 300 miles per charge. And I found that even driving from here to Mesa, Arizona, or Vegas, these are 6 hour drives roughly. You kind of have to stop and refuel yourself or relieve yourself.
Mhm.
And
Yeah.
just selecting a place to do that and charging the vehicle at the same time means that a vehicle, even with a 300-mile range, isn't hampering a road trip as much as you might have thought a few years ago.
Right.
Especially like if you had an 80-mile range Nissan Leaf or the electric Golf, for example, that was really challenging.
Mhm.
But if you've got a 300-mile range vehicle or 400-mile range vehicle, and you can use a lower cost battery, which has lower supply side challenges, something like iron phosphate. I think there's a good argument to be made for that.
Yeah, I mean, I always think like people want they just want this big range for this like one time a year that I'm gonna do this crazy thing and I want it, but the other like 99% of the time you just haul around this expensive heavy
Yeah.
battery pack that you're not really utilizing. So it is something that, it makes sense. So I think people will be happy to hear that you're thinking about that. How how difficult do you think it would be if Aptera decided to, you know, make a lithium iron phosphate battery pack? Like the cells are different shapes and everything, so you'd have to re-engineer an entirely different module and battery pack. Am I correct in
Well,
that?
you could go either way. You could just swap out the cells to be a different chemistry.
So they make
Um,
lithium iron phosphate in that same form
yeah,
factor?
yes,
Oh,
yeah.
okay. But the voltages
But
are different,
that's
right?
They are, yeah.
Uh-huh.
So the NMC goes from about 4 volts to 3 volts.
Hmm.
You wouldn't want to go much beyond 4.2 volts to maybe 2.6 volts.
Uh-huh.
So that's a pretty broad range compared to the 3.6 or 3.7 volt top for LFP, or iron
Uh-huh.
phosphate. So the top voltage of the battery is diminished. So that has perhaps some impact on performance of the electrical components, like the drive system may have less power available to it.
Hmm.
But ordinarily, the inverters, they can accommodate a much broader range, and
Hmm.
the LFP um, would operate sort of still in the fat part of the curve, right around where the NMC is operating. So the drive system in this case would operate normally. With the battery management system would have to have different settings put into it, but
Hmm.
all of the systems would probably be just fine. Probably wouldn't even notice a difference.
So am I understanding you correctly in saying that if Aptera decided to switch to LFP, it would not be that difficult to make that switch?
Well, it wouldn't need to be that difficult, but just changing from a cylindrical NMC cell to a iron phosphate cell is probably not the best solution.
Mm,
The better solution would probably be to go with a prismatic cell.
mm. The
And the reason
pouches?
for that, yeah, well, there are a couple different types of prismatic. Some of the prismatic will have pouches inside of them, stuffed
Okay.
into a little rectangular box, and others will have the individual sheets of material laid up in a stack, and then that stack is put into a box. Or some of them they call like a jelly roll.
Mhm.
They create a roll and then they squish the roll down and stuff it inside of a rectangular box. But the reason that would be preferable is it affords you a better packing efficiency. You get a better kilowatt hour per volume basis doing it that way. And when you're buying larger cells, the cost per kilowatt hour also goes down.
Okay. All right.
So the packaging efficiency increases and the manufacturing costs decreased.
And then how long do you think that would take to make that transition to is that's like a whole
I
new battery pack?
Yeah, I haven't studied it enough to give you a reasonable answer, but I think I can't imagine doing it in less than a year.
Okay. All right. Got it.
It would be a pretty big undertaking.
All right. Got it. All right. So some other common questions is can individual cells be replaced or serviced by the end user?
No,
Okay. That's can individual modules be removed and serviced and replaced by the end user?
I would say no, not by the end user.
Uh-huh.
Not because there's any physical barrier to doing that,
Uh,
but generally you wouldn't want to have an end user working on a 400 volt anything.
I see.
A service center like those that replace batteries in vehicles would probably be the best bet for that if there were a
Okay.
faulty module.
But a faulty module is designed to be replaced. You would have to replace the
Right.
entire pack because
Correct.
one module goes down. How does the, but individual cells are going to go bad. How does it, is there, can the battery handle a few cells going bad and still have the module function?
It can, though it would be at a diminished capacity. So these modules are constructed with the cells in a configuration where there are 24 cells welded together in parallel. And then that group is stuck into series with the next group of 24 cells. So if a single cell in a string, or sorry, not a string, if a single cell in a parallel group were to fail, you would have a diminished capacity of about 1/24th.
Yeah.
So it would be, what is that, maybe a 5% decrease in capacity. But the module would continue to perform normally if a cell had some internal fault that caused it to, let's say, maybe have an open circuit, for example.
Okay. All right.
And of course, it depends on the nature of the failure.
Yes. Yeah. Okay.
So sometimes they might fuse out if a cell had a internal short, then the wire bond that leads to it would open, and then it would just be isolated electrically, and it would no longer participate in the energy delivery.
Okay. And it's the battery pack modules are designed to do that.
Yeah,
Okay.
that's inherent in the design of a bus bar or current collector system.
Hmm.
The conductors are small enough so that if there's a fault, it should open the circuit rather than carrying enough current to do any kind of downstream damage.
I see. So the wire bonds or the bus bar will just like melt and like fall apart.
Just like a fuse element, yes.
Okay. All right. Okay, so more questions. Do we know the weight of one module and the weight of the entire battery pack?
I should have studied this before. No, I
Okay.
don't know off the top of my head. I think it's about 65 pounds per module
Okay.
times six.
Got it.
Um, so you do the math, and the frame probably 40 pounds, maybe 50 pounds.
Okay. All right. Do we know the use like what's the full kilowatt hour of the battery pack and what's the usable part of the battery pack?
Well, the full capacity, and this will depend to some extent on what cells we decide upon, because those little 2170 cells, they range from 4.8 amp hours up to about 5.2 or 5.3.
Hmm.
But it's generally around a 45 kilowatt hour battery pack.
Uh-huh.
44 if you're precise with your calculation. So we'd probably only want to use 38 or 40 of those hours in order to stay away from the very high end of charge, which causes excessive calendar aging, or the very low end of charge, which causes the batteries to degrade rapidly.
Okay, got it. Chris M came on Discord and he mentioned something about the number of cells in the module had to go down a small amount because some space had to be added. Can you talk to us about that?
Sure. Yeah, yeah. As I mentioned earlier, the frame contributes to some of the structural rigidity of the vehicle as a whole. So it participates in the crash protection in a sense. And one of the key things we need to be worried about is any intrusion into the battery pack, touching and rupturing cells. So by removing a row of cells from the module, we were able to get the battery, the outside edge of the battery further away from the outside of the vehicle, so that any deformation of the side of the battery and a side impact would not impinge upon the module, or hit any of the cells.
Okay. All right. Um, so the current battery pack probably do you think it will be upgradable to like LFP or different chemistries or different cells, or is the battery module and the pack design pretty custom to the chemistry and the cells we're targeting now?
Uh, Chemistry is an interesting one, because if you ask LG and Samsung and
Uh-huh.
Panasonic and EVE, ask any one of them what their chemistry is, the first thing they'll say is they're not going to tell you,
Uh-huh.
but they'll tell you that it's better than the other guys. So
Okay.
there's a lot of different chemistries within the NMC umbrella.
I see.
Um, and none of that makes any difference to us in
Okay.
terms of packaging. What makes a big difference is the form factor of the cells. So if we were to go with a lithium iron phosphate chemistry, for example, as I mentioned, we'd be better off changing the form factor of the cells to um, a either a pouch or a prismatic. And in that case, the existing battery design is not adaptable to that change. It would have to be redesigned internally, not
Okay.
not externally. We'd have to still fit it within the same frame of the vehicle, but the internal cross members and cooling plates and bus bars and all that sort of stuff would have to change to accommodate a different cell format.
Okay. Um, there's people have noticed that there's some kind of foam something that looks like foam that's being injected into the modules. Like, what
Yeah.
is the purpose of that foam and what is that foam?
Well, it serves a few different purposes. It actually is a thermal barrier. It provides some level of insulation from heat. If one cell were to go into thermal runaway, the function of that foam would be to prevent too much heat from radiating out and causing the adjacent cells to follow and go into thermal runaway. So that's one function of it. Another function is it encapsulates the fragile things like the current collectors. So it just has to barely touch those current collectors and stick to them, and that prevents them from vibrating under normal operating conditions. So that prevents them from breaking off. It also acts to bring all the individual cells in the battery together from a structural standpoint and sort of glue them together, so the system is more like a rigid brick rather than a sort of a imagine like a stack of playing cards. You got a bunch of things in there that are individually pretty flexible,
Hmm.
and you can bend the whole thing. But if you glued all those playing cards together, you wouldn't be able to bend it at all. And it does the very same thing for the battery module. It brings it together to make it structurally rigid, and it also helps to dampen any uh, vibration which would cause noise.
Okay. All right. I think one or two more questions and we're done. These are the questions coming in from Discord. Um, is there going to be a DC to DC converter to eliminate the 12-volt battery? Or are we going to always have a 12-volt battery?
Never say always, but the answer is no.
Okay.
We will not be eliminating the 12-volt battery. So much stuff runs on 12 volts.
Uh,
The lighting systems, the windshield wipers, the heater blower motor,
uh,
uh, all these things that are normal in automotive world um, are designed around a 12-volt battery, unless you look at something like the 48-volt system in a Cybertruck.
mhm.
But in that case, everything had to be designed from the ground up to work with the 48-volt system. So we're pretty far away from taking that leap at this point because it would mean that we'd have to design and build our own windshield wiper motor.
Yeah,
And that's not what we're about. We're focused on the broader high efficiency aspect of the vehicle, not the relatively unimpactful 12-volt system.
sure. So the 12-volt battery is charged by the traction, the motor, the large battery pack. Is that correct?
Yes, ultimately, all of the energy used in the vehicle comes from the big battery. But in the case of the 12-volt system, it does get recharged from
Mhm.
the through the DC-DC converter. Whereas in an internal combustion engine, you'd have an alternator. The DC-DC converter is similar in that it's providing power to charge the 12-volt system and keep it topped up.
Now, does that mean that the 12-volt battery can be relatively small
It
because
is
it can
very
constant?
small. Yeah, it's about this big and
Okay.
about that tall.
Okay. And what kind of battery is that? I'm guessing it's not a
It's
lead acid battery like in.
no, it's not. No, it's a NMC battery as well. And I think
Okay.
it's actually built with 18650 cells in it.
Okay.
I'm not positive, but it is a cylindrical battery on the inside, multiple cylindrical cells. And it has its own battery management system that protects it against overcurrent or overcharge, over discharge.
Awesome. All right. Is there anything that I should have asked you that I didn't?
Oh, I don't know. I didn't come prepared to answer that. I'm sorry.
Okay, no problem. All right.
You're the one who
Well,
provided the questions.
sure. Yeah, yeah. All right. Well, thank you so much for taking time out of your day to talk to us, Tim. These are the questions that the community has, and we appreciate your expertise and your time to talk to us about it.
Well, you're certainly welcome, and thanks for putting in all the effort to put these things together so everybody can see the same thing you're seeing.
All
I'm
right.
sure they enjoy it.
All right. Thanks, Tim. Hopefully, when I visit down there, I'll get to meet you in person.
Oh, certainly.
All right. Have a good day.
Thank you. Have a good day. Bye.